I would like to describe a field in which little has been done, but in which an enormous amount can be done. This field is not quite the same as the others in that it will tell us little of fundamental physics, but it will tell us much about the strange phenomena that occur just below our perception. In contrast to the natural philosophers of the past, the scientists of this field delve into the recesses of nature and show how she works in her hiding places. Their quest is to understand and create the imperceptible. After all, there is plenty of room at the bottom.
Hello and welcome to the Materialism Podcast, an exploration of the past, present, and future of material science and engineering. My name is Andrew, and I'm joined, as always, by my co-host, Taylor Sparks. And today we have a really exciting topic. It's one that we've been talking about for a while, but it was one of those that was so intimidating that we didn't think we could do it justice.
We teased this 3 years ago.
Probably. And
then we tried to put it together ourselves, and it was too intimidating.
Yeah, you read some of these papers, and you get maybe 2 sentences in before you have to start opening 5 tabs and Googling all of these things you've never heard of.
Today we are talking about quantum materials. And I would say in the world of sort of physics and chemistry and materials, this is the here be dragons sort of area. The types of compounds that they are cooking up here are things that I have never had a reason to explore before. And now we do have a reason to. They are made up of pretty exotic elements. So now is as good a time as any to be grateful that we have a sponsor like American Elements. This episode is brought to you by them. They are the world's manufacturer of advanced materials, AmericanElements.com, now Invent. They can help you actually fabricate some of these things. Okay, to help us understand this extremely difficult topic, we are joined by Jason Khoury of Arizona State University. He's a chemist out there, and in my opinion, one of the people that's going to really do a good job of breaking down complex stuff in ways that us mere mortal material scientists can understand. Jason, tell us about yourself.
Hi, nice to see everyone. My name is Jason Khoury. I'm an assistant professor at Arizona State University. I just started last year, August 2023.
Brand new.
And literally just started. My research focuses basically on chemistry approaches to quantum materials, like how we can use structure and bonding, like chemical bonds between different elements to understand these wonderful properties like superconductivity, complex magnetism, correlations between electrons, stuff like that. I'm associated with the School of Molecular Sciences at Arizona State and also the Center for Materials of the Universe, which is kind of a collaboration between geology and chemistry and materials, where we try to understand materials at extreme conditions like high pressure, high magnetic field, low temperature. Basically, if it's extreme or insane, we'll do it.
Very, very cool. And for people who care about that sort of thing, he comes from a pretty awesome – he's got the chops. He's got the background for this. He did his undergrad with Pat Woodward, his PhD with Mercuri Kanadzides, and then his postdoc with Leslie Shoup. So who better? Who better to talk about this? Jason,
thank you.
Maybe to kick it off, we're going to talk about, in this episode, an introduction to all things quantum materials. We're not going to go in depth on any of the specific technologies per se, but we want to give people the tools to understand those when we have those conversations later. So maybe as a starting point, what even is this notion that gets thrown around, quantum? Because we hear quantum everything. Quantum mania in the Marvel Universe. We hear quantum materials. We hear quantum information systems. What is this that we're talking about?
Yeah, it is kind of surreal to do research in this area and then see people talk about it like in entertainment or in the real world. And it's like sometimes it's similar to what you hear and sometimes
usually
it's
not though.
Yeah, usually not. But anyway, quantum materials brought down to like a very elementary level. It's a material with a property that cannot be explained by classical physics. Like you think classical physics, the ball rolls down the hill, potential energy, kinetic energy, whatever. This explicitly needs to use quantum mechanics or quantum physics, and that would involve basically things acting like both particles and waves at the same time. In this specific case for quantum materials, it's when you have interactions of electrons or orbitals or charge. So basically interactions between electrons and how they mess with each other, like with magnetism or with 2 electrons interacting through a phonon, which is called which can lead to a Cooper pair, which is related to superconductivity, or correlations between electrons where it should be a metal, but it's because the electrons are interacting with each other, it's actually insulating. So to sum it up, anything that is not related to classical physics that can't be explained that way is what a quantum material is.
Okay.
Yeah, because often as chemists or material scientists, we understand band diagrams, but maybe that's the closest we really get to quantum behavior within materials. And so would it be fair to say that these are materials where they basically defy our classical intuition in terms of how they're going to behave? And so properties and behaviors can emerge that are just unexpected.
Right. They defy our classical intuition. And in a lot of times they even defy our understanding of band structures. So there are some ways to use like adjustments or additional calculations to understand correlations in electronic band structures, like commonly was known as a U calculation when you're doing density functional theory, DFT. But even then, like, these are kind of approximations trying to get at how do electrons talk to each other? How do they interact? There's not one way of doing that.
And Jason, I'm kind of curious. Yeah, I know that you mentioned like superconductivity is one, instance of where we need to use, where we would describe as a quantum material.
Yeah.
And I know that one we don't fully understand, at least not all different types of superconductivity. I'm curious with all the other aspects of. Do you disagree? First off, and then secondly, like, are all of these things sort of similarly misunderstood, or do we now have a pretty good grasp of how these different things work, or are we still figuring them out?
It's definitely case by case. For superconductivity, you're definitely correct. There are some things we don't understand. So there's like the original theory that people discovered in the 50s and 60s from John Bardeen, Leon Cooper, and John Schrieffer.
BCS.
So if people know BCS literally stands for Bardeen, Cooper, Schrieffer. It is their theory for their mechanism of superconductivity. And then maybe in perhaps kind of silly, there is what's called unconventional superconductivity, which is essentially an umbrella term for literally everything that's not BCS.
We don't get how it works. Hopefully we will soon.
Yeah, I think it's kind of a strange characterization, and I'll leave it to a superconductivity expert that you have on at a later date to really go into it. But basically, like, we understand BCS reasonably well, but we don't really understand a lot of unconventional things. We don't understand are there different unconventional mechanisms that can lead to high temperature superconductivity at reasonable pressures. You can get some at really high pressures, but other stuff like that. For other things like electron correlations for complex magnetic phases, as you can kind of guess, magnetism is basically a black box. Like, we understand certain things about it in certain contexts, but not in others. Or we might struggle to understand chemical intuition for why do we have this magnetic phase and not this one? Or it's just, it really is like, how deep do you want to dig the rabbit hole?
Okay.
So with that in mind, and without the ability for there being any sort of unifying theory across these many different behaviors, is it very much a cook and look approach to finding these? Are a lot of them found by accidents, or is there enough theory that we can at least guide explorations to try to find materials or physical contexts for these to emerge?
Yeah, this is an awesome question. So in some cases, there are theories. People might predict that a certain material or certain material property might exist, like a material that exhibits a property or just the property itself. And sometimes, like, it might just take the right person or the right experimental group being able to verify it, or verifying like the spirit of it, but maybe it's a little different around the edges. But oftentimes, especially with like higher temperature superconductors, they tend to be accidents, like found on accident, like the cuprates. They were a serendipitous discovery. People didn't know what the phase was. The physicists were able to find superconductivity in this phase fraction, but they didn't quite know which one was it. And then once they got it, it was hard to understand because those compounds had defects and vacancies. Yeah. So there are lots of cases of serendipitous discovery, and then there are cases of we theoretically predicted that this would happen, and then we finally found the material systems to experimentally verify it. Topology, which is another set of quantum materials that I won't totally get into, was predicted by some theoretical physicists at the University of Pennsylvania in the mid-2000s, and I think even before that in the late 90s. And then some material systems like graphene or bismuth selenide, bismuth telluride, then started getting experimental verification of these phenomena.
Well, before we get too far into this, maybe we can back up a little bit and try and understand what are the key components we have to understand quantum materials. You've mentioned a couple times now correlations and interactions. So do you want to describe what are we talking about? What do we mean by correlations? Exactly what types of interactions are being leveraged in these quantum materials?
Yeah, so when I say correlations, for the layman or layperson, it's basically like, are electrons interacting with or talking to each other, or are spins interacting with and talking to each other? Like, spins interacting with each other can be typical magnetic phases, a ferromagnetic, where both spins are pointing up. antiferromagnetic, where spins are anti-parallel to each other, or ferrimagnetic, where they're opposite but not quite equal, like one spin magnitude is stronger than the other. Those would be examples of spins interacting with or correlating with each other. With electrons specifically interacting with each other, it would be like the Cooper pair in superconductivity, where because of a phonon, like a packet of sound mediating this interaction, they're sort of correlated with or attached to each other, and they have a particular correlation length, which is kind of like the length or distance between them and the Cooper pair. That's one type of correlation. Another would be what's called heavy fermion, where these very local moments are screening other electrons around them, and that makes them appear to be way heavier than they actually are. So there's like different flavors of how it comes forward, but the way I think about it is these are all like ensemble characters or ensemble actors in the same play. Like, they might have different roles, but they're all part of the same production.
Okay, so if I'm hearing you right, there's two types of interactions that you've described so far. That can be that the spins interact with one another or the charge themselves. What else is there? Are there other types of interactions that we leverage in these types of materials?
Yeah, one big one that I've sort of alluded to are like lattice interactions. So is your audience familiar with what a phonon is? Basically a packet of sound or
Go ahead and
heat.
explain it just in case.
Okay, a phonon is kind of just like a quantized packet of sound or heat, and phonons can be used to mediate different interactions in quantum materials. The common one that we talk about is superconductivity, but there are also another one called an electronic instability, where electrons interact with each other in a way that opens a energy gap in an electronic band structure. That's often referred to as a charge density wave, though people nitpicking will say that sometimes that's not actually what it is. But the main point is phonons often interact with electrons for electron-electron interactions. They're like middlemen or mediators between them.
I see.
So that's a lattice interaction. But and then for orbital interactions, that's just degrees of orbital overlap. It's kind of hard to have a quantum material when all your bonds are ionic. You need to have decent orbital overlap, decent band dispersion, and then that'll leave mediation for electrons to move around, electrons talk to each other, stuff like that.
So that makes sense, because when you look at the periodic table on most of these quantum materials, it's not drawing from like the edges like you would find in ionic materials. It's in these like a lot of them are main group elements where you're getting them and that's because of the orbital degree of freedom that it gives you in providing an interaction.
Yeah, for sure. And I mean, with the case of like lead or antimony, the stereoactivity of the lone pair can lead to different unique structures, and those structures can modify the electronic band structure in a way that's different than something where the lone pair is not expressed. So there's lots of chemical questions too, like how does structure lead to function, and how does structure lead to the electronic structure? How do we like find that link between crystal and electronic structure, as you would say?
And what role does crystal symmetry play in this?
A lot. But I mean, I think you've told your audience about electronic band structure before, but essentially the link between crystal structure and electronic structure is crucial for understanding solid state chemistry in general, not even to mention quantum materials. So if you have covalent bonds in solids, you would have long dispersive bands where there's a large energy discrepancy when you go from one point in momentum space to another. And those, like how dispersive or lack thereof your bands are, dictates all of your properties. And then applying correlations on top of those, like orbital or orbital interactions, can lead to some other quantum material properties too. And then also like for magnetic band structures, over a certain point, if it's like say it's an antiferromagnetic transition, the band structure will change because all these bands will originally be like doubly degenerate, then they'll split in symmetry, and then you'll have all these extra bands in the band structure. That's called Fermi surface reconstruction. So changes in magnetic structure can change your electronic band structure too.
Okay. Well, and I just got finished teaching it in my grad level intro to materials class. We talked about tensors, and It's like this whole awful thing on tensors that nobody likes to learn about. But the whole point is that at the end, like, hey, we just learned about symmetry, underlying symmetries leading to point groups and space groups. And then there's Neumann's principle that says the symmetry elements of a physical property of a crystal must include the symmetry elements of the space group of that crystal, right? Because so often if you look in the back of your introductory material science book, it says the thermal conductivity is what it is. And sometimes it blows these students' minds when I tell them, like, that's not like a single value. That's like for the bulk polycrystalline material. actually the properties depend and they inherit the symmetry of the underlying crystal. And I imagine that in a lot of quantum applications where you are growing single crystals, you're not dealing with necessarily polycrystalline materials, that directionality, that inherent symmetry is something that we leverage in creating these devices.
Yeah, I'm so glad you brought this up. This is really in my bag now. When you're measuring these different properties, when you're going down to 2 Kelvin in our physical property measurement systems, the goal is a lot of the time is to grow good enough single crystals that you could put contacts on them if you're measuring its resistivity, or align them in certain directions. And we want to try to measure them along the A, B, or C axis, or different crystallographic planes, depending on if it's hexagonal or trigonal or something like that. So it's one thing if you open a book and you see a property in like a table for a polycrystalline powder system, but the value of that coefficient might be very different if you measure along A, B, or C in an anisotropic system. And a lot of the times for magnetic systems, magnetic anisotropy is crucial to finding what's the easy axis of magnetization.
Killer.
That's right. I mean, there's that really famous plot of all of the measurements of copper thermal conductivity, and it's like all over the place to the point where you might even question if we actually know the thermal conductivity. Of course we do, but it just goes to show how much diversity in terms of property measurement there can be for the same material. And I guess one question I have is relating to this is, in theory, there's all of these various quantum effects that are happening, but to actually verify them, we have to measure them in these materials. And how do we go about that? Is that something pretty easy to do, or have we had to develop a lot of new characterization techniques to access this information?
So this is a cool thing where there are different schools of thought in how people approach this. There's there's like Maya and chemist approaches where it's like, let's try to make new materials or discover new materials with particular structural motifs, like particular arrangements of bonds, where we'd expect a certain type of electronic structure based on its crystal structure and go for that. There's kind of the more physicist approach where it's like, let's grow crystals of known materials that we know what the symmetry is. Mm-hmm. We have an idea of what the properties are. We know what the magnetic elements are, and then tweak it by tuning it, doping it, alloying it, putting it under pressure, under strain, under high fields, applied magnetic fields, high electric fields, and then see what goes on with that. And then there's kind of the engineering approaches where it's, let's make a device, let's kind of have coincident cooperating 2 materials or 3 materials cooperating with each other in a device, or let's try to measure properties like in the aggregate. So there's lots of different ways to do it, and they all tell you different things. Like one can tell you how to make different materials, one can tell you how to measure them properly, another one can tell you if they're practical in devices or for technology or not. And that's even, I would say, a simplification. They all meld together, but it's all super cool how people approach things differently.
And maybe what are some of these techniques that people are using? So X-ray and neutron diffraction for sure.
Oh, you know the quote from Paul? It's so good.
Oh,
the
illicit love child one.
Oh, yeah.
oh God. Okay.
There's also the one about potatoes.
There's a review article in Reports on Progress in Physics from Paul Canfield, a very talented physicist at Ames Lab at Iowa State, or in conjunction with Iowa State. And he has a line in it where it's like, condensed matter, or new materials physics is basically an illicit love child between condensed matter physics and solid state chemistry with a material science foster parent. And
which is just what you described.
Yeah, pretty much. This is not new for him. He writes whimsically like this in all of his stuff. You can go find it. But he actually has another really important line where he talks about how to understand new materials physics, where he says you must be bilingual in the languages of bonds and bands. So you have to speak both languages. You have to know what chemical bonding looks like and have good chemical intuition. But you have to understand band structure too. It's not mutually exclusive. It's not chemists do one thing only and physicists do one thing only. We all have to work together if we're going to make this work.
And we're hearing that even in this episode. There's jargon and words being thrown out, which are clearly some from the chemistry community and some from the physics world. And hopefully, material scientists can be there to kind of bridge that gap. But I think it's important for people to learn that language, right? And how did you, what your background was chemistry as an undergrad. Kanadzides is also a chemist. Shoup's more of a physicist. Was it difficult to transition over?
She's a chemist too. She's a chemist too, actually. So It's weird. I actually have no formal physics background at any level. Like my BS, my PhD, my postdoc were all with chemists, but I kind of found myself nudging towards this path. Like I remember when I was a graduate student in Mercuri Kanazides' lab at Northwestern, and I was doing metal flux synthesis, basically reactivity methodology. How do we make these materials better? So with flux, it's like, in the same way water dissolves sugar, metals at high temperatures dissolve other metals, and we don't understand that as well as we should. That's the gist. But I remember talking to some of my mentors, they were all chemists too, and I'd ask them things like, oh, what does this do? Like, what properties does this have? Is there any way we can predict that? And a lot of the time, like, bless their hearts, they would be like, oh, I don't care. I'm like, oh, really? You don't care? Like, why not? So and like Mercuri was interested depending on which property it was, and he did a great job with that. But our goals were a bit different. Like I was interested in some more of these electronic things. He was interested in like functional materials, like thermoelectrics. How do you convert heat to energy? Solar cells for perovskites. You know, all the cool stuff. But we all have different paths, I guess.
Cool. Very cool to hear.
Yeah, that Paul Canfield article, we'll definitely put it in the show notes. It's worth a read, if only for his various almost poetic explanations of various conceptual topics in this field.
We don't see enough writing like that in material science, physics, or chemistry, right? With that sort of verve and grace, it's actually fun to. You don't just want somebody to tell you about the paper; you want to read the paper.
Yeah,
you want them to make you excited about reading the paper.
That's it.
Mm-hmm.
And I actually asked Paul at a conference, like, "Oh, your writing style is like pretty whimsical. Like, why do you write that way?" Or I mean, I thought it's cool. Like, I'm just curious what the thought process was. And he said back that a lot of people in chemistry and physics can be very Germanic in their writing, which has its uses. Like, people want the facts and they want the story and they want it in a succinct way and cut all the other stuff out and just give me what I need. But we all got into this because we like science, I would say, or we even dare say we love it. So we need to express that love in a way that gets people excited about doing science.
Amen.
And if we write in a way that inspires people, I think that's a good thing. If we tell people that this is cool and here's why you should think it's cool too, that's a good thing. Like, I think quantum materials are cool. I think they could lead to different developments in technology. I love, like, for example, I love trains. I would love a superconducting maglev train that goes throughout the entire North America and the US and everything. Let's make it a reality. Let's get higher temperature superconductors and let's do it. But yeah, there's a lot of different things you can do.
Well, you're preaching to the choir. We believe in being excited about material science and telling people about it.
Maybe to return to our earlier conversation about trying to identify or measure these properties, what sort of specific characterization techniques are being used? XRD and neutron diffraction make a lot of sense for the phase and the structure.
But you got to be measuring transport, right?
Mm-hmm.
So this is a great question. I'll break it down. For structure, you want to do X-ray diffraction, either powder with powders or single crystal with as-grown single crystals if you can get them of good quality. For magnetic measurements, you want to do neutron diffraction, either powder or single crystal. Same thing, depending on if you can grow powder or single crystal. For characterization of like the morphology of a crystal or its elemental analysis, you want to do scanning electron microscopy or energy dispersive X-ray spectroscopy, otherwise known as EDS or EDX. If you want to do properties, though, you would use you can either use a home-built setup for resistivity or magnetization or specific heat capacity, or you can often use what we call a physical property measurement system from quantum design. Otherwise known as the PPMS. It's basically a cryostat with a bunch of fancy attachments, and the fancy attachments can measure resistivity, magnetometry of all sorts, like AC and DC susceptibility, specific heat capacity, so like normal heat capacity or long pulse heat capacity. You can measure them under magnetic fields, but from all of these you can see down to 2 Kelvin or even lower than 2 Kelvin if you have special attachments, different magnetic transitions, structural phase transitions, electrical transitions, any transition under the sun pretty much. But with a lot of quantum materials, all the interesting stuff, all the action is down at low temperatures, usually below 100 and often below 50 Kelvin. So a lot of the time, we just measured some materials recently, their transitions are at like 5 Kelvin, if you want an idea of what the average one looks like.
Yeah. So you said diffraction, basically, either X-ray or electron or neutron to look at the structure. But there's also spectroscopy, right? Because you've been talking a lot about the band diagram, the band structure. That's not an easy thing to access, but we do have tools, ARPAs, if you want to describe that, or other tools out there that allow us to visualize and understand band structure.
Yeah, ARPAs is basically a way to visualize band structure. It's its own full technique, and it can be difficult to measure. The reason being that you need to cleave a crystal in vacuum. So if the crystal is layered like a 2D material, you can cleave it fine. Like that works. Even if it's 1D, you can sort of cleave it. But if it's 3D, if the crystallinity isn't great, like if it's hard to grow crystals of it, like just because you can grow a crystal of something doesn't mean you can cleave it. It's tough.
Is that the problem? Is because if you have to have under vacuum because stuff will stick to the surface, and ARPAs is just like a super surface sensitive technique. Is that the issue?
It's a surface technique. The surface needs to be pristine, so you have to cleave it in vacuum. And even if you cleave it, if you don't get a good cleave, the surface is the data will just look terrible. Like you won't get good data for it. So it's just hard to do. And I don't personally have background experience in ARPAs. I've always worked with collaborators if we have done it, and bless their hearts, like it's tough. Yeah.
Well, just some of the things you've described, I know experts that do just that thing, just neutron diffraction, just single crystal diffraction, just do PPMS, transport measurements. Yeah. These are hard. I remember coming into, I was a new postdoc at Santa Barbara. I showed up and Ram Seshadri, God bless the guy, I just love him. He tells me, he's like, Taylor, I want you to build this magnetoelectric measurement system. It shouldn't be that hard. And I was just like, yeah, man, let's do it. And I was in for a world of hurt, dude. That was crazy hard to do. We were building our own custom device that was going inside a PPMS and was measuring capacitance. Basically, it was basically just trying to get a capacitance bridge. Which now that I've done it, it's like, okay, it wasn't that hard, but to not know anything about that and to just like assume that I've got a PhD in materials or physics, I guess it was applied physics, I can tackle this. Dude, it was so hard. And it was stuff that I didn't even know to think about. Like I was using copper wires, and yet you're down at like 2 Kelvin, and copper's an awesome heat conductor, and it's like pouring heat into this, and I couldn't figure out what was going on. Or like I wasn't using shielded wires, and I didn't realize like, what do you need to shield your wire? Like it was just a serious learning curve. So when you say that like these quantum materials require this breadth of different characterization techniques, does that mean that this is inherently always going to be team science? Or are there really like Tony Starks out there that can just like do all the things? Or is in your experience, like, is this really like a setting for team science?
It's a perfect setting for team science. I mean, there are different approaches, kind of like when we were talking about physics versus chem versus MSc earlier. A physicist will be more likely to focus on one technique, or a set of techniques within a certain umbrella. Like you have transport physicists, you have ARPAs physicists, you have dedicated time resolved ultra-fast spectroscopists. But even then, and then you have chemists like us who focus on synthesis or characterization or kind of turning out new materials and trying to find relations between them. But this is always going to be a team effort between theorists, experimentalists, engineers, scientists of all stripes. I think, especially in the modern age of science, your best skill is your communication skill. It's how well you get to know other people, how friendly you are, how much you're willing to work with people. Just 2 hours before this, I was on a Zoom call with a collaborator about an experiment we're going to do together. Stoked about it. I think it's going to be great. But this is so much of a group effort. Even in my own lab with my young lab with my one student so far, a lot of it is if I don't know something, I have to set him up with someone who does. So as a PI, your job is to help that person succeed. It's not for you to make sure that person succeeds. You need to make sure that someone can help them succeed.
I love it. So speaking about, your background is a chemist. Tell me about some of the things that you do in the field of quantum materials. Because chemist is about molecular design principles, right? It's about understanding mechanistic from a bonding, from a reactivity standpoint. How do you bring that to bear in designing or working in quantum materials?
Yeah, so as a synthetic solid state chemist by training, my emphasis was just on all forms of synthesis. I primarily focus on metal flux, so high temperature metal becomes a liquid, dissolves something else, kind of like what I was saying earlier. But we do other techniques too. We do direct combination, like the exact stoichiometry trying to make a certain material. we do what's called chemical vapor transport, where you have a gaseous transport agent that takes your different elemental reagents and then carries them from a hot end to a cold end of a tube and grows crystals from nucleation sites like scratches on the tube or seeds and stuff like that. But the main thing with me is it always comes back to synthesis. If you make a material that hasn't been made before, you have to use crystallography, single crystal often, or powder to solve it. If it has been made before and it's like you're tweaking it, like you're putting in alloying or doping in some other element, how is that different? How is that changing the lattice parameter? And then how does that change the properties? Are we changing the electron count? Are we keeping the electron count the same? So everything for me is just how do we make insert new material here, and then how do we find out what it does and how it fits into all this interwoven tapestry of quantum materials.
And so when you look at the periodic table, do you look at it now in the interest of exploring quantum effects differently than you would have as a solid-state chemist? Or I guess what's the intuition there and how does that change? And if it doesn't change, why not?
No, it's an awesome question. I would say that yes, because I emphasize certain parts differently. Earlier, we were talking with Taylor about main group elements and how they're good for covalent bonding. So I would obviously prioritize main group elements like indium, gallium, bismuth, something like that over like alkali and alkaline earth metals like lithium, sodium, barium, calcium. But also, if you want to focus on different types of magnetism, you need to find where the unpaired spins are. So if you want the early transition metals, cobalt, chromium, vanadium, those 3D transition metals. But if you want really localized F orbital magnetism, then you want the lanthanides. So cerium, praseodymium, samarium, neodymium, ytterbium, terbium. Even in Paul's review article, he talks about different parts of the periodic table. There's a figure for it where it's like sharp orbitals, diffuse transition metal orbitals, main group. When you look at the periodic table, regardless of what type of chemistry research you're doing, there are going to be some elements that kind of like are worth your while and some that are a little bit less so. And then some that are toxic that you just don't want to work with no matter who you are. But like, I don't want to do thallium ever. But the main thing is that it does affect how you look. Yeah.
Maybe to talk about another important tool in the chemist and materials science toolkit is phase diagrams, which, you're talking about growing these materials. Well, a lot of materials are non-trivial to grow. Just because you can predict something has a certain property, actually coming up with the synthesis pathway to get there is quite challenging. And now, normally we just look at phase diagrams in terms of maybe binary, ternary, just in terms of elements. But here you're dealing with pressure, you're dealing with magnetism and the magnetic fields that they're under, maybe even the electrical fields that they're under. So how do you use phase diagrams in this field to not only design, but look for new materials?
Yeah, great question. I look at phase diagrams pretty much every day. And as a metal flux person, I actually look at them almost in terms of solubility. So if I'm going to dissolve something in like liquid tin or liquid indium or liquid bismuth, I will look at binary phase diagrams between indium and iridium, or bismuth and cobalt, or bismuth and ytterbium, and I'll see when do they both become like a homogeneous liquid. So if you look up at this temperature, reagent 1 becomes a liquid in bismuth as an example, and then reagent 2 becomes a liquid at like 1,000 degrees, but the other one becomes a liquid at like 900 degrees. Then you have to go to 1100 C, and then they're all dissolved in there. So I kind of see it as almost like a solubility guide. So does one metal dissolve them at reasonable temperatures that you can go to? And then you can cool down from those temperatures and hopefully grow out some crystal that incorporates all of the elements.
Dude,
so in that way, I use phase diagrams as like a solubility tool.
I would love to tag onto that. We did the same thing. So I've been working in the field of quantum materials for almost 10 years now, but not understanding what I'm doing. I'm just making the stuff for my physics homies that need it. They say, hey, we need a single crystal of material X. And I'm like, I could probably make that. And we usually don't know how to make it. And we usually look in literature to see how somebody else did, and we try and copy theirs. And a good example of that is BSTS. So BSTS, we're going to talk about it in a later episode when we get on topological materials, but it's bismuth, it's selenium, it's tellurium, it's antimony. And when you look in the literature, the way that they have all been cooking this is like 850C. Like there's something magic about 850C, but everybody does it.
Too, yeah.
Everybody does it. And so we were looking at this. And one of the problems is you've got 4 different elements. You can see it in the ampule that there's clearly like evaporization. There's volatilization and then evaporation and condensation of some of your more volatile elements. And so your stoichiometry goes off. And so we figured out lots of tricks to prevent this. Like you just fill up the headspace for one thing, like stuff a bunch of quartz wool in there or like a plug. Like getting rid of the headspace fixes this problem a little bit. We tried a bunch of different stuff. But then I had this student of mine, Hussein, who's great. And he's like, Professor Sparks, why don't we just do like CalFad modeling? CalFad is calculated phase diagrams. That's what it stands for, right? And I was like, yeah, I guess why not? He's like, all we have to do is figure out the temperature where it's all melted at. And sure enough, like if you look at the vapor pressure, you can actually calculate these things or measure it yourself. You see that the vapor pressure of selenium, that's the real troublemaker, just goes nuts after like 500 degrees. And the other ones are much more stable. And yet when you calculate the CalFad phase diagram of this, we found, again, and it's only as good as like the CalFad software is at modeling that system, which is a big if, right? But we showed that we should be able to get all liquid by just over 300 Celsius. Like this is like crazy lower than what's been done. And so we actually tried it. We grew a bunch of these things at a variety of temperatures, and sure enough, we were able to get a bunch of single crystals at way lower temperatures. So to answer Andrew's question, like phase diagrams are awesome, and tools for generating phase diagrams where we don't yet have phase diagrams are awesome. They're, I think, pretty indispensable in exploring new materials with funky chemistries.
Oh, I was going to say, just one of the most important thing is that a phase diagram is useful to tell you where things might melt or might solubilize or might come together, but it's always like a suggestion of reality. Like you never know when you have 3 or 4 or even 5 elements in, what's the actual melting point? Where are they actually going to come out with compounds? And people try, people make computational predictions, but they don't substitute doing the actual work and trying to figure out what's going on for real. Yeah. And sometimes with these black box setups where you have tubes, you can't watch it when it's in the furnace unless you have like one of those setups where you can watch the stuff become liquid, but most people don't. So you really got to trial and error your way into figuring this stuff out. Different max temperatures, different reagent ratios, different heating profiles, cooling times, like how long you dwell at certain stages. It all matters.
Yeah.
Yeah, I mean, many phase diagrams are still undergoing changes, like even binaries, as they're finding either new compounds or, finding more precise melting and solidus and liquidus lines.
Right. Actually, one funny thing that Taylor mentioned about the 850 degrees C as like a sweet spot for a lot of bismuth chalcogenides. If you look back at a lot of old solid state literature, and I mean like old as in before 1990, but even around there's a lot of like, oh, we left it in there for 356 hours. We waited 17 and a half days. And I was like, I would ask people at the time, why did they say 17 and a half days? And I'll never forget, some older mentor was like, probably went on vacation for 17 and a half days.
Yeah,
and then came back and took it out of the furnace. Or they forgot about it in the furnace and then they took it out. It's like, well, it worked. I guess we're going to have to do 17 and a half days from now on. Like that stuff,
dude, like that's bias everywhere or just in the literature.
Yeah. It's not like we haven't gotten over it. There are lots of things where it's like, oh, we'll put it in for 4 days and then cool it for 12 days. And I'm like, why do you need 12? Why not 6? Why not 4.5? Mm-hmm. It's like, that's just the way we've always done it.
Well, think about it. There's so much you have to do these, like from growing the crystal to characterizing, make sure you're right, to measuring the properties to it's hard and it's already team science. And now you're going to say, hey, by the way, we should really fully explore the growth region. Like I get why people don't want to do it. It's a lot of work and it's hard. We're all trying
Decision
to get PhDs
or
whatever, right? And so like there's a lot going into there. And you maybe only have so many furnaces. We run into that all the time. We've got 2 Bridgman furnaces and they're running around the clock. And there's lots of experiments I'd like to run, but like these growths take like a month. So it's tricky.
Furnaces are a valuable resource.
Or even having like the right furnace for the job. When I was out in industry, I did a lot of work with hydriding, and the phase diagrams for hydrides are not that great, especially if you're looking for more detailed information on phases and their specific properties and when they form and the necessary vapor pressures and such. It can be pretty tricky. If you're in industry, they're not going to spend the resources to explore these either.
Something we're facing here at Utah is we don't have a laser. We don't have an optical furnace, right, for growing oxide single crystals, and we want to real bad, right? So we can grow non-oxides, but if you need oxygen as a reactant, we can't do it right now, and we're hoping that we can get that. So yeah, definitely there are unique tools to this field, and some of them are non-trivial to use and implement.
Yeah, I mean, also tools are getting better all the time. Like, I wasn't like 5-ish years ago, an electron diffraction instrument was very unique if you had it at a university. Now you can get a almost benchtop electron diffraction instrument anywhere. When I was in graduate school, we had an old school single crystal diffractometer that McCurry had in the lab, and it would collect on an image plate, like one frame at a time for single crystal diffraction. And that would take hours, if not days, for good collections of lower symmetry.
Yeah, dude.
Now it's like a powder X-ray diffraction pattern. You can get it in 10 minutes, 8 minutes, 20 minutes if it's a higher symmetry thing. It's insane how much quicker and how much easier we can gather information now and gather data.
Yeah.
There's one thing I do want to mention, Taylor. I do think it's hilarious that Ram mentioned to you that this was going to be an easy project, because I wanted to interject saying, like, any PI that says to a graduate student or postdoc, I have an easy project for you, like, run for the hills. That project is not easy. The easy project is the one that takes you completely by surprise, where it just works and you're like, I'm lucky.
My favorite quote,
I did. It's not being smart. Yeah.
So Hayden Evans, who I'm sure you know, he always talks about Tony Cheatham. They were on a former episode. Check out our episode on carbon sequestration materials on ALD. But he talks about something. He's like, hey, Hayden, come along, 20-minute adventure. It's going to be super fun. No big deal. You're going to love it. It's like not a 20-minute adventure. Several years of my career, and now I'm working on this years later. So, yeah. But it's good. It's good to be challenged, and it's good to have PIs who instill you with foolhardy courage sometimes to go face what would otherwise be really daunting areas like quantum materials.
You got to be genuinely optimistic if you want to be an academic. Like, don't get me wrong, I love my job. I'm really privileged that I get to do this that people actually pay me to like mentor students and teach people and do research. Like, it really is the dream, but you gotta kind of have like a bit of a thicker skin to realize like, oh, this isn't going to amount to much, or, oh, this compound's kind of boring, or, oh, we're in like a multi-year lull where people haven't really found anything super cool. You just got to hope that the next cool thing is around the corner, or you're not going to get through it.
Yeah. Or, oh, I was just telling Andrew before this call started, I write, on average, probably 10 grants a year, and one gets funded. That's just how it goes.
Yeah. I mean, like when you're talking about the optical furnace or whatever, like you get on that equipment grant, I guess. Maybe if you try it 5 times, you'll get it funded once.
That's right.
Yeah.
Maybe one last question that comes to mind about this field. What is the role of computational methods in furthering this space and helping us identify new materials? Is it really feasible to simulate some of these emergent behaviors, or
I guess to clarify, is this explicitly a AI question, or is this just a computational in general question?
Computational in general. It could be anything from DFT, thermo, to maybe machine.
Okay. And we've already heard about CalFat. I think CalFat is a good example of helping you in the design space. How are people using DFT extensively in this area? Like, you've been talking about a lot of band diagrams. Yeah. That is a great way to get diagrams.
People use DFT. They use type binding models to model the electronic structure of different motifs. They try to use calculations as a tool to help them either make small scale predictions of, like, instead of looking in an ocean, I'll look in a river or a pond, or to rationalize the data they've already collected. Like, we have this cool property, this cool structure. Now we're going to use calculations to explain its properties, its bonding, other stuff. I think of computation as a valuable tool, and there are some things for predicting different phase equilibria or predicting structures altogether. That stuff is improving and getting better, but it'll probably take time for it to fully get there in a way that can help us. So. But the future of all computation, in my opinion, and the present, is that it exists in tandem, complementary with experimentalists, helping a feedback loop back and forth of each person doing their job better. It will not be one takes over the other ever.
Yeah, I completely agree. And I especially believe from like an AI standpoint, it's that data of multimodal sources, right? Using simulations where it makes sense, experiments as ground truth where that makes sense, and modeling based off of that is certainly my perspective.
Make my job easier. That's like the goal of all of these computations. Make my job easier, make my job more streamlined, help me out. That's all you got to do.
maybe just a for fun question, are there any exciting developments that have happened in this field that the general public isn't aware of? Like, are there things that excite you that aren't being, blown up in pop science journals or magazines?
I don't know if it's really been, I think it's been blown up a little bit, but I personally thought, even though I don't work on it, that the twisted bilayer graphene stuff, where they were making different moire patterns, for people that aren't familiar, there's like normal solid state symmetry. And then there's this kind of like special symmetry where you have one sheet of a material on top of another sheet of material at a particular angle, often called a magic angle. And it creates what's called a moire symmetry that's not accessible via normal crystallographic space groups. They recently found that there are superconducting transitions in moire patterns of graphene. So it's called twisted bilayer graphene for short. There are problems too. Like, it's kind of like bubble wrap on top of bubble wrap. You got to get a perfect area of the device where they're layered on top of each other and not crumpled up. It's not that easy to scale, but you can actually change the carrier concentration or voltage without doping or introducing vacancies. I think it's a great tool to help us learn some fundamental science. And I think maybe the average person might not be as familiar with it, even though it's been a thing since about 2018, 2019. It's really cool. It's interesting. It's not something I personally want to do, but I think I'm really happy to see people doing it.
Okay, Jason, we could go on. We could go on, and we intend to. We intend to have actually that this is going to be a mini-series on quantum materials. Today was the primer.
I love it.
We hope that it's going to be providing the tools for people to understand the subsequent conversations on superconductors, on quantum computers, on quantum sensing, on all these other things that we hopefully will get to. We hope that this will be a good touch point to get them going. And Jason, we appreciate it because we don't understand this stuff, and we appreciate you breaking it down for us.
Thank you so much for your time. I hope this was helpful. And if anyone's ever interested if any of the watchers are interested in the research that we do or what you guys do, just reach out with questions.
Absolutely. Okay. Thanks, Game. I will talk to you later. Today's episode is brought to you by American Elements, the world's manufacturer of advanced materials. American Elements now invent. We also want to point out Materials Today. They have been an amazing sponsor for a very long time. Thanks to Materials Today, we can keep producing this show. We hope that you'll check out materialstoday.com to stay updated with the latest happenings in the material science field. Read some of their great articles. They are a high-impact publisher, which means they get really interesting articles there, people that are really pushing the boundary. I find myself reading there quite often. So check out elsevier.com, materialstoday.com, and check out their books, conferences, and other programs. And lastly, we're always grateful for the other things that make the show possible, like the music. You can find Alphabot and Kolobyte on iTunes and elsewhere, so we'd appreciate if you check them out. And we would always love if you would give us a review. That will teach the algorithm that other people should also listen to this. So give us a hand. You can actually leave us comments or reviews, iTunes, Spotify, YouTube, wherever you listen to your podcast, we are found there. And if not, tell us, and we will get there. And lastly, just interact with us directly. If you got an idea for an episode, want to shoot us an email, we are materialism.podcast@gmail.com, or you can find us at materialism.podcast on Instagram and chat with us. Okay, thanks so much.
Yep.
The inventors of fire, electricity, magnetism, iron, lead, glass, silk, cotton, the makers of tools, the captors of lightning, the architect, the engineer, the musician, are all beneficiaries of the materials of this world and are bound only by their imaginations in manipulating those materials.